Hi everyone, this is Dr. Chao Luo from the University of Miami. Today I'm very glad to talk about our research related to organic electron materials for affordable and sustainable sodium-ion and potassium-ion batteries. One of my research interests focuses on developing affordable and sustainable organic batteries because of the low cost and high abundance of organic resources. We are very interested in design and synthesize the organic electron materials for fast charging and sustainable batteries. I have worked in this field for over a decade. Initially, we developed a number of carbonyl compounds and applied those carbonyl compounds in lithium-ion and sodium-ion batteries. In 2018, we introduced azo chemistry into the battery field and reported the first azo compound in alkaline-ion batteries and all solid-state batteries. After 2019, we started to work in the field of redox-active polymers and reported one-dimensional, two-dimensional, and three-dimensional polymers and applied them in alkaline-ion batteries and multivalent metal batteries, aiming to increase the battery performances and sustainability. And recently, we are especially interested in developing organic sodium and potassium-ion batteries because of the low cost and high abundance of the sodium and the potassium resources in Earth's crust. Moreover, the redox potential and the capacity of the sodium and the potassium are comparable to lithium. This makes sodium and potassium-ion batteries promising alternatives to lithium-ion batteries. However, there are still challenges for sodium and potassium ion batteries. First is the larger ion size of sodium and potassium ion. This will trigger larger volume change and worse reaction kinetics. Second is the more complicated nucleation chemistry of sodium ion and potassium ion. This will result in worse performance in sodium and potassium ion batteries in terms of specific capacity and cycle life. So my research interest focused on developing advanced organic electron materials to achieve high performance sodium and potassium ion batteries because of the high structure tunability and abundant structure diversity of the organic materials. However, there are still challenges for the organic batteries. First is the volume change induced particle polarization. The organic particles suffers from volume expansion and shrinkage during the sodiation and dissociation process. After long-term cycling, the organic particles will be pulverized into small pieces, and the pulverized particles will become inactive. This will cause the capacity loss of the battery. To address this challenge, we synthesized organic nanowires to decrease the particle size of organic materials from the microscale to the nanoscale. In this way, we can effectively mitigate the particle polarization and achieve high-performance organic batteries. Second challenge is the poor electronic conductivity. Most organic compounds, they suffer from low electronic conductivity. So when we prepare the organic electrodes, we need to add a large amount of conductive carbon, usually 30 weight%. So this will increase the electronic conductivity of the electrode. But during the long-term cycling, there are volume change of the active material. This will not only cause the particle polarization, but also make the active material lose contact with the conductive carbon black. To address this challenge, we leverage the self-healing chemistry between the organic active material and the polymer binder. So here we use the hydrogen bonding between oxygen in active material and hydroxyl group in the polymer binder to retain the structure integrity of the organic electrodes. In this way, we can achieve high-performance organic sodium-ion batteries. And the third challenge is the high solubility in the electrolyte. Most organic materials, they are either soluble or slightly soluble in the electrolyte. So they can dissolve from the working electrode into the electrolyte and then diffuse from the electrolyte to the contact electrode. At the contact electrode, the chemical reaction instead of the electrochemical reaction will take place. This will cause fast capacity fading. To address this challenge, we synthesize carboxylated azo compound. Here, we intentionally introduce two carboxylate function group into the azobenzene to increase the polarity of the material and reduce its solubility in the electrolyte. In this way, we can achieve high-performance organic sodium batteries as well. Recently, we started to work in the field of redox-active polymers because when we polymerize the organic compounds to form polymers, the solubility of the polymer will be decreased with the increase of the molecular weight. So in our first work, we synthesized 3 linear polymers, PNA, PPAI, and PBAI. If we compare their structure, they all contain the azobenzene moiety and the carbonyl moiety. And when we compare the structure, we can see they have the same azobenzene moiety, and the difference is in the carbonyl moiety. So here in PNA, it contains the naphthalene ring, while in PPAI, it contains the benzene ring. In the PBAI, it contains the diphenyl group. Here, we want to study how the conjugation structure impact the polymer cathodes in sodium-ion batteries. So we apply them in sodium-ion batteries and test under same condition. We can see all 3 polymers show reversible charge and discharge behaviors. Well, if we compare their redox potential, the PNA with the large conjugation structure, the naphthalene ring, shows the average redox potential at about 2.2 volts, while for PPAI and the PBAI, their redox potential are below 2 volts. So from here, we learn that the extended conjugation structure can increase the redox potential of the polymer cathodes. And then we further compare their cyclic stability. The PNA also shows the highest stability among the 3 polymers. So these results demonstrate that PNA has the best performance among the 3 polymers, and the extended conjugation structures, naphthalene ring here, improves the redox potential and the cyclic stability of the polymer cathodes. So we further study the reaction kinetics of the PNA using the rate tests and the CV on the various scan rates. In the rate test, the polymer was cycled from 50 milliampere per gram to up to 10 ampere per gram. So we can see they can be actively cycled from low current density to high current density. And after that, we return the current back to 50 milliampere hour per gram. The initial capacity can be recovered immediately, demonstrating robust reaction kinetics. And then in the cyclic voltammetry on the various scan rates, we calculated the stable value for the cathodic and anodic peaks. They are at 0.91 and 0.86. Since this value is closer to 1, means the reaction kinetics is controlled by the pseudo-capacitive behavior. So from this, we learned that the extended conjugation structure in the polymer increase the electrochemical performance in sodium-ion batteries. So in our following work, we further extend the conjugation structure from the naphthalene ring to the pyrene ring and synthesize the polymer using the polycondensation method. And here, this polymer, PTAD, also contains the azobenzene moiety and carbonyl moiety. And then the reaction mechanism is as follows. The 2 carbonyl groups in the polymer can reversibly react with 2 metal ions and the electrons to reduce the CO double bond to CO single bond. And then the nitrogen-nitrogen double bond can further react with metal ions and the electrons to reduce the azo group to nitrogen-nitrogen single bond. So this electrochemical reaction provides energy for the battery, and we test their performance in sodium-ion batteries. We can see the PTAD polymer delivers 2 pairs of redox plateaus centered at about 2.3 volt and 1.5 volt. The redox plateaus at 2.3 volt responds to the carbonyl reaction, while the redox plateaus at about 1.5 volt corresponds to the azo reaction. And the reversible capacity, about 180, can be delivered at a high current density of 500 milliampere per gram. And then we also test the cyclic voltammetry. We observe multiple redox peaks in the CV, and these redox peaks are well matched with the charge and discharge behaviors in this figure. And then in the long-term cycling test, this polymer delivers a great cycle life of 1,400 cycles with high capacity retention and high Coulombic efficiency, demonstrating excellent cyclic stability. And in the rate test, we also increased the current density from 50 milliampere per gram to up to 10 ampere per gram. And then we reduced the current density back to 50 ampere per gram. So the polymer cathodes can be cycled at up to 10 ampere per gram, and after that, its capacity can be recovered immediately, demonstrating fast reaction kinetics. And the kinetics is further studied by the cyclic voltammetry, GITD tests, and the EIS test. So in the cyclic water temperature test, we also calculate the slope value for the cathodic peaks and anodic peaks. And here, this value are in the middle of 0.5 to 1, which means both surface reaction and the diffusion reaction contribute to the fast kinetics. In the GITD test, we discharge the battery for 30 minutes and then rest for 3 hours to observe the overpotential during the discharge and the charge. So here we can clearly observe a very small overpotential indicating fast kinetics. In the ES test, we observe small depressed semicircle here, and this semicircle is very stable from pristine to 50 cycles, demonstrating a low interfacial resistance, and the formed interface is very stable upon cycling. So from all the results, we know that the PTAD polymer shows high performance in sodium-ion batteries at room temperature. To extend its application, we further explore the performance at low temperatures. So before we perform the low temperature test, we screen the electrolyte and identify that the sodium PF6 in DME electrolyte is suitable for the low temperature test. And we prepare the electrolyte with the concentration from 0.5 mol to 1 mol. And we place those electrolytes in a low temperature oven at a minus 50 degrees C for 24 hours. After that, we opened the chamber and found that the 0.5 mol electrolyte is still in the liquid state, but the electrolyte with higher concentration are partially freezed. So we decide to move forward with this low concentration electrolyte. And we also checked the electrochemical stability window of this low concentration electrolyte. It is stable in the cutoff window of the polymer cathodes. And then we couple the low concentration electrolyte with our polymer cathodes and test the battery from room temperature to minus 50 degrees C. We can clearly observe that the redox plateaus for carbonyl reaction and azo reaction are retained when we decrease temperature to minus 50 degrees C, while the capacity is decreased to 140 milliampere hour per gram. That's because of the slower reaction kinetics at low temperatures. And then in the cyclic test at various temperatures, we can see when we decrease the temperature from room temperature to minus 50 degrees C, the capacity is slightly decreased. While after we return the temperature back to room temperature, the initial capacity can be recovered immediately, demonstrating good reaction kinetics, even at low temperature. While the cyclic stability was evaluated at low temperature of minus 50 degrees C, these polymer cathodes can deliver and retain the capacity for 150 cycles with high Coulombic efficiency, demonstrating excellent cyclic stability at low temperature. So from here, we know that this polymer cathode is promising for sodium-ion batteries at both low temperature and room temperature. And then we further study the reaction mechanism using XPS and the Raman spectroscopy. In the XPS, we can see the azo peaks in the sodium 1s spectrum. During the discharge, this peak disappears and the new peak for the sodium nitrogen bond forms. While during the charge, the peak for azo group can be recovered, demonstrating reversible azo redox reaction. While in the Raman spectrum, we observe the stretching evaporation for the azo groups in the pristine electrodes, while during the discharge, the 3 peaks disappear, while during the charge, the peaks can be recovered, demonstrating reversible azo reaction as well. In the oxygen 1s spectrum of XPS, we also observe the appearance of the CO single bond after discharge, but it retains during the charge, means the interface contains the CO single bond. But here we do observe the peak intensity change during discharge and charge, suggesting the carbonyl reaction. And in the fluorine 1s spectrum, we observe the formation of the sodium fluoride peak after discharge, and it is retained during the charge, indicating a sodium fluoride-rich interface formed in the polymer cathodes. So from here, we confirms the reversible azo redox reaction and the sodium fluoride-rich interface for this polymer cathode, which are important for the high performance in sodium-ion batteries. From these studies, we know that the linear polymers could be promising for sodium-ion batteries, but their redox potential, capacity, and cyclic stability are still limited. To further improve those electrochemical performances, we also studied two-dimensional and three-dimensional polymers. So we synthesized the PHATN, and initially we evaluate the performance of HAT and HATN. We found that those small organic compounds, they are either soluble or slightly soluble in the sodium-ion battery electrolyte. And then we decided to polymerize the HATN to form the PHATN, which is insoluble in the electrolyte. And then we measure the property using XPS, TGA, FTR, and BT. In XPS, the polymer shows an amorphous structure. In TGA, the polymer is stable at up to 200 degrees C. In FTR, we observe the imine function group in the polymer. And the BT result shows a surface area of 384 meters square per gram, and the total pore volume about 0.27 centimeter cubic per gram, demonstrating a porous structure. And then we apply this polymer in sodium-ion batteries. Here is the proposed reaction mechanism. The imine function group can reversibly react with sodium ions and electrons to reduce the CN double bond to CN single bond. Well, this electrochemical reaction delivers the redox plateaus centered at about 2 volts. It's a sloping plateau. And in the cyclical atometry, we observe multiple pairs of redox peaks. They overlap with each other, resulting in the sloping plateau in the charge and discharge curves. While in the long-term cycling tests, the polymer cathodes deliver a good cycle life of 100 cycles and high Coulombic efficiency at C/8 current density. And then we collaborate with Dr. Oleg Bardin to perform the computational methods to study the reaction mechanism between the imine group in the polymer and the sodium ions. And then we observe the step-by-step interaction between the imine group and sodium ions. The calculated redox potential are well matched with our cyclical atometry result, confirming the reaction mechanism. And then we also perform the GITT to study the reaction kinetics, and we observe a very small overpotential indicating fast reaction kinetics upon cycling. And then we further study the kinetics using the radical-velocity tests. We increase the current density from C/8 to 25 C and then return to C/8. We can see the battery can be cycled at high current density of 25 C, and after we return the current back, it can recover its initial capacity immediately, demonstrating fast reaction kinetics. And then we compare the performance of this polymer cathodes with the other organic electrode materials in sodium-ion batteries. Its power density and energy density outperforms of most other organic electrode materials in sodium-ion batteries, demonstrating a promising cathode for sodium-ion batteries. And then we further test the high current density performance of this polymer cathode at 25 C, and we can see they deliver a ultra long cycle life of 50,000 cycles with high Coulombic efficiency, demonstrating excellent cyclic stability and high and fast charging capability. And then we check the charge-discharge behaviors after long-term cycling. Their charge-discharge behaviors are still retained. And we also check the dissolution of the material before and after cycling. We didn't observe any dissolution of the material in the electrolyte. So from all these results, we confirm that the PHATN polymer exhibited high reactivity and high cyclic stability in sodium-ion batteries. To further confirm, we increased the mass loading of the active material from 2 milligram per centimeter square to 10 milligram per centimeter square. So even at a high mass loading, the material can still retain its reversible capacity for 500 cycles, demonstrating high performance in sodium-ion batteries. And then the reaction mechanism was studied using XPS, FTIR, and the Raman spectroscopy. In XPS, when we discharge the material to 1 volt, we clearly observe the peak intensity decrease of the imine group, and also we observe the appearance of the sodium-nitrogen bond in the XPS spectrum, indicating the reaction between the imine group and sodium ions. And then we recharge the material back to 3.5 volt. The sodium-nitrogen peak disappears, while the imine peak can be recovered, demonstrating the reversible reaction between imine group and sodium ions. While in the FTIR and the Raman spectroscopy, we clearly observe the peak intensity change for the imine group during the discharge and charge. And then in the Raman spectrum, we observe the appearance of the sodium-nitrogen bond. So from all these results, we confirm the reversible reaction between the imine group and sodium ions. So these results shows that two-dimensional polymers are promising cathode for sodium-ion batteries, but this polymer cathode only deliver the redox potential at about 2 volt, which is low compared to the inorganic counterparts. To increase the redox potential, we started to work on bipolar polymers recently. So we developed the polymer with the diamine moiety and the carbonyl moiety. Here we intentionally introduced 4 conjugation structures into the carbonyl moiety to further confirm how the conjugation structure impact the electrochemical performance. Here we use benzene ring, diphenyl group, naphthalene ring, and the pyrene in the carbonyl moiety. Here is the proposed mechanism. The diamine moiety can react with ions and electrons. This ion insertion reaction will provide high redox potential but suffers from low specific capacity. To increase the specific capacity, we further introduce the carbonyl group into the polymer to enhance the capacity, because the carbonyl groups can react with metal ions and electrons. And then we test the performance of the 4 polymers in sodium-ion batteries under the same condition. We observe that they can deliver 2 pairs of redox plateaus, one centered at about 3.6 volts, and the other one centered below 2.5 volts. So the redox plateaus at 3.6 volts corresponds to the ion insertion reaction between the diamine moiety and ions from the electrolyte, while the plateaus below 2.5 volt corresponds to the carbonyl reaction between carbonyl groups and sodium ions. Here, if we compare the redox potential of the 4 polymers, we can see the polymer with larger conjugation structure, PNT and PPT, they show the redox plateaus at about 2.2 and 2.3 volts for the carbonyl reaction, while for the polymer with smaller conjugation structure, PPM and PPP, they deliver the redox plateau below 2 volt for the carbonyl reaction. So this results further confirms that the conjugation structure is critical for the redox plateau of the polymer cathodes. And then we further compare their cyclic stability. The polymers with larger conjugation structure show good cyclic stability, but the polymer with smaller conjugation structure suffers from fast capacity loss in sodium-ion batteries. So from here, we further confirm that the extended conjugation structure is critical to the performance of the polymer cathodes in terms of redox potential and cyclic stability. Since the PNT and PPT show good stability in sodium-ion batteries, we further apply them in more challenging potassium-ion batteries. So they deliver the redox plateaus for the carbonyl reactions at about 2.4 volts in potassium-ion batteries, while we didn't observe the redox plateaus for the ion insertion reactions, probably because the electrolyte that we use does not support the ion insertion reactions in potassium-ion batteries. Well, we also check the cyclic stability. The polymer suffers from fast initial capacity loss in the first 20 cycles, and then they become stable in the following cycles. And in the rate tests, the polymer can be cycled at up to 5 ampere per gram, demonstrating fast reaction kinetics. So from here, we know that the bipolar polymer could also be promising for developing sodium and potassium batteries. But the stability of this bipolar polymer is still limited. So we further developed 3-dimensional polymers to introduce more cross-link structures and porosities into the polymer to enhance their cyclic stability. So here we use a 3-dimensional linker there is a sp3 carbon here to make the three-dimensional polymers. And we only connected the carbonyl reaction with the linker in the first study. And then since we know the conjugation structure is important to the performance, so we only use the naphthalene ring and the pyrene ring for the polymer cathodes. And then we test their performance in sodium-ion batteries first. They deliver the redox platos for the carbonyl reaction with reversible capacity about 100 milliampere hour per gram. And the CV results are well matched with the charge and discharge behaviors. And then we further test the cyclic stability and rate capability of PTP in the sodium-ion batteries and potassium-ion batteries. So this polymer delivers a good cycle life of 8,000 cycles in sodium-ion batteries and 1,000 cycles in potassium batteries, demonstrating superior electrochemical stability in sodium and potassium batteries. In the rate tests, the polymer can be cycled at up to 2 ampere per gram in both sodium ion and potassium ion batteries with high capacity retention, demonstrating fast reaction kinetics. So from this result, we confirm that the three-dimensional polymers can be promising cathode for sodium and potassium batteries, but the capacity and the redox potential of this polymer cathode is still limited. So in the future, we will try to incorporate more function group, cross-link structures, and the conjugation structure into the three-dimensional polymers to further improve their electrochemical performances. And finally, I would like to give you some take-home messages. So in our work, we developed one-dimensional, two-dimensional, and three-dimensional polymers with multiple functional groups as organic cathodes for sodium-ion and potassium-ion batteries. When we increase the dimensions, there are more cross-linked structures in the polymer, which mitigate the dissolution of the material and also make the multiporous polymers. This will increase the cyclic stability and the reaction kinetics. We also systematically studied the impact of extended conjugation structure to the performance of polymer cathodes in sodium-ion batteries and demonstrated that with a larger conjugation structure, the redox potential and the cyclic stability of the polymer cathode will be improved. And finally, we developed a carbonyl and azo-based polymer cathode and coupled it with a low concentration electrolyte. This types of batteries also shows high performance at both room temperature and low temperatures. And finally, I would like to acknowledge my collaborators from following institutions. They provide great support to my research, and also my group members. They also make great contributions to the growth of our group. And then finally, I would like to thank the funding support from George Mason University, ASF, and the University of Miami. Thank you for your attention. I would like to take any questions. So if you have any questions, please send me an email or leave a message. Thank you. Bye-bye.